I'm Dr. D.K. Tripathi, an assistant professor of physics under the Department of Basic Science and Humanities. So we have learned the nanomaterials and its properties in last two lectures. In third lecture today, we will see some of the nanomaterials or engineered nanomaterials. But before that, a naturally occurring seed, which is called as graphene seed, we'll discuss at first. So in the last class, we have seen that what is quantum uh, tunneling, and we also come to know that what is uh, quantization of electrons. So that we have discussed. Today we will use that. Now, graphene. Graphene is the naturally occurring seed. Actually, graphene is a class of material which is allotrope of carbon. Uh, Up to 1991, we were knowing about only three allotropes, or you can say that three classes of basically three classes or three major allotrope of carbon. That was carbon itself, diamond, and graphite. But in 2004, Andrei Jim and Konstantin Novoselov from University of Manchester discovered graphene. What is the beauty of this? We will discuss, but I'm telling you that this is the thinnest as well as strongest material in the world. No material is as thin as this one, and it is the strongest material in the world. So graphene is an atom thick honeycomb seed. You see what happens actually in the carbons. We know that in carbon has the catenation property. Catenation property means one carbon atom can join with other carbon atom. So this is very good thing about the carbon, and that is why you have seen that, or you have learned that there are 10 lakh of materials which are made of carbon, and that is why organic chemistry is taught to you. So because of its catenation property, what happens in the graphene, a very large number of carbon atoms are attached to each other. At least 60 atoms are attached, otherwise that cannot be called as the graphene sheet. So graphene is an atom thick honeycomb sheet of carbon atoms, and it is the building block of other graphitic material. That means those materials which are made of graphite, it is the building block of that. What we come to know from that, that it is the, you can say that a very smaller fraction or very smaller part of graphite. That means if you go to the lower level, or if you reduce the dimension of graphite, then you'll find the graphene sheet. Since a typical carbon atom has a diameter of about 0.33 nanometer. Okay, carbon atom is having how much um, diameter? 0.33 into 10 power minus 9 meter. And there are about 3 million layers of graphene in 1 millimeter of graphite. You just think, in 1 millimeter of graphite, there are 3 million layers of graphene. So you can understand that how small this graphene sheet is. And what is the beauty of this graphene sheet? This graphene sheet is harder than diamond. If it is harder, this does not mean that it is not elastic. It is more elastic than rubber. So flexible. It is very much flexible. And it is tougher than steel. You see, these are the peculiar properties. And also, it is lighter than aluminum. So all these four properties are in it. And at bulk level, all these properties are just the opposite properties. But at nano level, a material that is graphene, which is harder, is also elastic. A material which is tougher is also lighter. Just to realize it, if a sheet of cling film, like kitchen wrap film, had the same strength as pristine monolayer of graphene, it would require the force exerted by a mass of 2000 kilogram. That means if 2000 kilogram force will apply or a large car will be placed on this layer, then it will be punctured. Okay, so its strength is very high. Now, other peculiar properties of graphene: it is having high electron mobility. How much? Nearly 100 times faster than silicon. We know that the mobility of the electron of silicon is very high, and the mobility of graphene sheet, the mobility of electron of graphene sheet is 100 times faster than that. The high conductivity of heat. This graphene is having high conductivity of heat, 2 times better than diamond. High electrical conductivity, 13 times better than copper. We know that copper is the second best conductor of the world. Silver is the best conductor of world and copper is the second best. And the conductivity of this graphene is 13 times better than copper. And very good thing about it is that it absorbs only 2.3% of reflecting light, and other light, or out of 100%, only 2.3% will be absorbed and the whole will be reflected back. So it's very good reflector, and it is optically transparent. This graphene sheet is optically transparent. And also one thing about very good about this is that impervious in nature. So what happened? The smallest atom, that is helium, He24, mass number is 4 and atomic number is 2. That is the smallest atom other than hydrogen, cannot pass through a defect-free monolayer graphene sheet. Its high surface area of 2630, that means 2630 square meters per gram, means that with less than 3 grams we can cover an entire saucer field. This means that we need 6 grams only, okay, to cover up this 2630 square meter per gram area with the help of graphene sheet. It is new class of material. This graphene was invented, I told you that, in 2004. So it is a new class of, this Andrejim and Konstantin Novoselov has got the Nobel Prize for this year for invention of graphene. So it is a new class of material that is only 1 atom thick. Only 1 atom thick means if the atoms are arranged in only 2 dimensions, that means in X and Y, or length and breadth dimension, or Y and Z, there is no dimension of X. That means breadth or height direction. That means only 2 directions. So it is a new class of material that is only 1 atom thick. So it is a 2-dimensional material. It can extend in only 2 dimensions, length and width, or you can say that width and height. At the material is only 1 atom thick. The 3rd dimension, height, is considered to be 0. Now you see, graphene is 2-dimensional material. That means a sheet can be formed with it. Okay. So graphene is used for the fabrication of mixed dimensional van der Waals heterostructures that could be carried out through hybridizing graphene with 1-dimensional quantum dots. 0-dimensional quantum dots. We have learned this, that quantum dots are 0-dimensional. No dimension of it is in the bulk range. All the dimensions are in the nano range. So if we hybridize graphene with 0-dimensional quantum dots or nanoparticles, or 1-dimensional nanostructures, so 2 dimension it have, and if we use 1-dimensional nanostructure, then it will have 3-dimensional, or it will become 3-dimensional bulk material. Because what is the concept? The concept is that any 3-dimensional object can also be treated as the nanomaterials, that it is made of very small or in the nanomaterials, and if the array of nanomaterials in all three directions x, y, z is making the bulk body. Now quantum wire or nanowire. You see, a quantum wire is an electrically conducting wire in which quantum effect influence the transport properties is seen. Okay, last day we have discussed that what is quantization, what is quantum effect, what is quantum confinement. So quantum wire is an electrically conducting wire in which quantum effect or quantum confinement is seen. Now you see, if the diameter of the wire is in the nano range, then electron will experience quantum confinement. Yesterday we have discussed in the second chapter or in the second lecture. So quantum confinement will be in the transverse direction. Because of that, the transverse energy will be limited to a series of discrete values. Then the formula of the resistance R equal to rho L by A, where R is the resistance, rho is resistivity, L is the length, and A is the cross-sectional area, will not be valid in the quantum wires, because only one dimension of it is seen to us. Only the length direction and other directions are not available. So electron can move in the length direction only. And if electrons are confined in the length direction only, then its property will not be same as the bulk body. An exact calculation of the transverse energies of the confined electrons has to be performed to calculate a wire's resistance. Hence, from the quantization of electronic energy, the electrical conductance, what is electrical conductance? The inverse of the resistance, is found to be quantized in multiple of 2e square h, where E is the electronic charge and h is Planck's constant. So the factor of 2, this factor, arises because of the spin degeneracy. We know that electrons are having two spins, minus half and plus half. So because of that, it comes twice. So from material to material, it is dependent on the electronic properties, especially on the effective mass of the electrons. Okay. Now in practice, semiconductors can show clear conductance quantization for large wire transverse dimensions of nearly 100 nanometer, because the electronic modes due to the confinement are spatially extended. You see what happens in the nanowire or quantum wire, only one dimension is seen. So electron is confined to move in only one dimension. In other dimension, it cannot move. And because of that, the peculiar properties of conductivity will arise. What happens last day, we have discussed that the band gap will increase. And because of increase of this band gap, the property will be, conductivity property will be different than at the bulk level than the nano level. So from metals, quantization corresponding to the lowest energy state is only observed for atomic wires, their corresponding wavelength being thus extremely small. You see, their corresponding wavelength will be comparable to the diameter because of the quantum confinement. So have a very large energy separation. I told you that band gap will be increased, which makes the resistance quantization observable. Where at the room temperature also, that means nearly 27 degrees centigrade to 30 degrees centigrade. At that, you can see the thermal properties or thermal conductivity will be different. Now, applications of nanowires. Silver chloride nanowires are used as a photocatalyst to decompose organic molecules in polluted water. If you want to decompose the organic materials in the polluted water, what we will have to use? We will have to just put the silver chloride nanowires. Silver nanowires are used to kill bacteria in the water. Nanowire mats are used to absorb oil. If there is any oil, that can be absorbed with the help of nanowire mats. Okay, nanowires are used to build transistors without PN junction. You see, this is very, very important thing, or you can say a new advancement in the field of electronics, that without using any PN junction, No junction is required. Nanowire can act as the PN junction diode. Can act as the transistor. That means in place of PN junction, we know that PNP or NPN transistors are there. So what happens? We are taking the pure semiconductor, and on which what happens, that P type or N type doping is done. Okay, so that is not required. Using the nanowires, the transistors can be fabricated, PNP or NPN, anyone. Nanowires made of an alloy of iron and nickel are used to create dense memory device. You see, memory devices we have learned before this nanomaterial. They can be built up using nanowires. Which nanowire? Alloy of iron and nickel. Why? Because iron and nickel both are ferromagnetic material. So they can store the memory, they can store the data. Silver nanowires embedded in polymer are used to make conductive layers that can flex without damaging the conductor. So without damaging the conductor, it can flex. That means it is having the flexibility. Sensors using zinc oxide nanowire detection elements are capable of detecting a range of chemical vapors. So these are some of the applications of nanowires. Carbon nanotube. Carbon nanotube is such a fascinating subject that nearly 1 lakh of papers are published per year on this. And if Howrah Bridge is made of this carbon nanotube, that will last for million years. So you can say that this is the strongest material. I told you that graphene is the strongest material, and this carbon nanotube is made of graphene. This carbon nanotube was invented by Sumio Lizima in 1991, before the graphene. So the concept of carbon nanotube was given by Sumio Lizima in 1991, before graphene, whereas it is made of graphene. Now you see, this is a diagram of single wall carbon nanotube, SWCNT. You see what happens, that a graphene sheet is there, and if it is rolled up, so it will have this structure. Okay, the diameter of this single wall carbon nanotube is 0.5 to 1.5 nanometer. And this is multi-walled carbon nanotube. That means different walls are there. You see, this is one wall, this is the another wall, this is the another wall, multi-walled carbon nanotube. In spite of that, its dimension cannot increase than 100 nanometer, because it is to be in the nano range. Carbon nanotubes are cylindrical molecules. You have just seen, it is cylindrical molecule. So are cylindrical molecules that consist of rolled up sheets of single layer carbon atoms. I told you that is graphene. They can be single walled, maybe multiple walled, consisting of several concentrically interlinked nanotubes. You see, this and this both are having the same center. This is also having the same center. So concentrically, single walled carbon nanotube is inserted so that it can have the structure of multi-walled carbon nanotube, and it should be within 100 nanometer. Like their building block graphene, carbon nanotubes are chemically bonded with sp2 bond. In the graphene, there is sp2 hybridization. So here also there is sp2 hybridization, an extremely strong form of molecular interaction. Probably you have heard this or learned in the chemistry. This feature, combined with carbon nanotubes' natural inclination to rope together via van der Waals forces, provide the opportunity to develop ultra high strength, this is very important thing, low weight materials that possess highly conductive electrical and thermal properties. The rolling up direction that is called as chiral vector. Chiral vector of the graphene layers determines the electrical properties of the nanotube. So on the basis of rolling up direction, the electrical properties will be decided. Chirality describes the angle of nanotubes hexagonal carbon atom lattice. Okay, so armchair nanotubes. They are called so because of their structure. Their shape is like armchair. That is why this is called as armchair nanotubes. And they are highly desired for their perfect conductivity. Their conductivity is very, very high. They are unlike zigzag nanotubes. There are two types of nanotubes, armchair and zigzag. So they are unlike the zigzag nanotubes. Okay, turning a graphene sheet a mere 30 degree. If you turn the graphene sheet to 30 degree, just only 30 degree, will change the nanotube it from armchair to zigzag. Then armchair will become zigzag nanotube. So multi-wall carbon nanotubes are always conducting and achieve at least the same level of conductivity as metals. Okay, although it is made of carbon, we know that carbon is bad conductor, but at nano level it becomes the conductor. Not only that, multi-walled carbon nanotubes are always conducting and achieve at least the same level of conductivity as the metals. Their conductivity is like the metals, at least, or more than that. It may be possible. So these carbon nanotubes, what are their properties? Let us describe one by one. They have high electrical conductivity. Their thermal conductivity is better than that of diamond. Their mechanical strength is very high. Their mechanical tensile strength can be 400 times that of steel. You just think. Mechanical strength is so high. They are very lightweight. Their density is 1/6 of that of the steel, and they have a very high aspect ratio greater than 1000. That is, in relation to their length, they are extremely thin. Okay, length is, if length is 1000, then the breadth will be 1. So aspect ratio is length to other dimension 1000 to 1. That means they are extremely thin. That means their other two dimensions are falling in the nano range. They are highly chemically stable and resist virtually and chemical impact unless they are simultaneously exposed to high temperatures and oxygen. And this property makes them extremely resistant to corrosion. That means carbon nanotubes are resistant to corrosion. That is why I told you that if Havra Bridge is made with the carbon nanotube, that will last at least for 1 million years. This is because of this fact. Their hollow interior can be filled with various nanomaterials. You see, they are having hollow structures. Okay, so it can be filled with several materials. So if you want to produce the nano drug, you can put some material inside it and that can be given to the patient. Okay, so separating and shielding them from the surrounding environment, a property that is extremely useful for nanomedicine applications like drug delivery. Due to all these properties, the carbon nanotubes are best for electronic devices, chemical, electrochemical, and biosensors, transistors, electron field emitters, lithium-ion batteries. Lithium-ion batteries, you know, nanomaterials are used there, and that can be charged quickly and that will not discharge quickly. That will last for longer time. White light sources, hydrogen storage cell, cathode ray tubes, electrostatic discharge, all these are there. Now, some of the applications which has been done. Eastern Bell Sports Incorporation have been in partnership with Jivex Performance Materials. And what they did, they have used this carbon nanotechnology in number of their bicycle components like flat and riser handlebars, cranks, forks, seat posts, stems, and aero bars. And these cycles are costly also. Don't think that this will be available in low cost. Amroy Europe OI manufacturers Hyptonite. They have used also the carbon nanotubes So to form the composite material that is 20% to 30% stronger than other composite materials. It has been used to wind turbines, marine paints, and variety of sport gear such as skis, ice, hockey sticks, baseball bats, hunting arrows, and surfboards. Carbon nanomaterials are also used for atomic force microscopic probes. And in tissue engineering, carbon nanotubes can act as the scaffolding for bone growth. This is very important thing. So these are used. Now we come to know that what is the use of carbon nanotube. In the next class, we will only concentrate over the use of nanomaterials in different field. It may be environmental field of environment, or it may be the field of electronics. Where it is used, we will discuss only that. So these are the references. You must go through these references, and thank you.